Now let's see a special case of the Metropolis-Hastings algorithm, and that's known as the Metropolis algorithm. The MH sampler is actually a generalization of an earlier version of the method, which is known as the Metropolis sampler. The Metropolis sampler is characterized by a symmetric proposal density, where g of x given y is equal to g of y given x. An example of this is the random walk Metropolis sampler, in which g of y given xt is equal to a function evaluated at the absolute value difference between xt and y. Let's provide a more specific example. For example, if we use the proposal y given xt follows the normal distribution with mean xt and variance sigma squared. In this case, we know that the density for g is given by 1 divided by square root of 2 pi times sigma times e to the negative y minus xt squared divided by 2 sigma squared. In this case, you can see that g of xt given y is equal. We just flipped the y and the xt in the normal density. So by implementing a symmetric proposal density, this allows us to simplify the acceptance probability in Metropolis-Hastings sampler. The two g's on the numerator and the denominators cancel out, and we're left with an acceptance probability of the minimum of 1 and the ratio between fy and fxt, where f is the target density we want to draw from. Let us try to apply this random walk Metropolis sampler to generate draws from a target distribution, which is the student t distribution with new degrees of freedom. The density is given by this formula over here, which I will definitely not try to read. And the proposal distribution G we will use is y given xt follows the normal distribution with mean xt and variance sigma squared. So the density looks really complicated. However, you can see that a lot of them are constants with respect to x. So the gamma function here and the gamma function here do not actually involve x. So when we calculate the ratio between fy and fxt, we can actually cancel out the constants, and we were left with the acceptance probability of the minimum of y and the ratio of just this part that involves x. So for this example, let's try to do a Monte Carlo simulation study. We will first create a function for the Metropolis sampler. So the inputs of the functions include the degrees of freedom of the t distribution, which we denote by nu in the formula, the proposal standard deviation sigma, that is what we use as the standard deviation for the proposal distribution with mean xt, the chain length n, and an initial value x0 for the Markov chain. We will also, for simplicity, use dt, which is the built-in function in R for the density of the t, to compute fy and fxt, so we don't have to hand type the formula ourselves. And we will see how the choice of sigma for the proposal affects the samples as well as the acceptance rate. So here's the function, which takes inputs degrees of freedom, sigma, x0, and n. And what it does is that it implements the Metropolis sampler. The code is quite similar to the Metropolis-Hastings case we have seen before, where we first create a zero vector of length n to store the Metropolis draws. The source value will be equal to the initial value we feed in, which is x0. And outside of the loop, we create a vector of u's, which are uniform 0, 1 draws of length n. So instead of drawing a single number in each draw, we will just use the corresponding entry in this u vector. We'll also create a k, which is currently equal to 0, to store the number of accepted proposals. Every time we accept a y, we will increment k by 1. The rest of the code is quite similar to before. So starting from the second iteration, we will first generate y from the normal distribution with mean that's equal to the last x, xt minus 1, and variance sigma, which is the sigma parameter we feed in for the variance of the proposal distribution. Then we compute the acceptance probability, which we denote by ratio over here. That's given by the t density with new degrees of freedom evaluated at y, divided by the t density with new degrees of freedom evaluated at the last t, the last x, xi minus 1. And if the ith entry of the u vector, which is a uniform 0, 1 draw, is less than or equal to this acceptance probability, then we will accept the draw, increment k by 1, and set the ith x to be equal to the current y. Otherwise, we will reject. So if accept is equal to 0, then the ith iteration of x will be equal to xi minus 1, which is the last x. This function will return a list which contains the x's and the k. So the x's are the draws that we have obtained using the Metropolis sampler, and k is the number of iterations that we have accepted. So let's try different choices of sigma. And without loss of generality, let's assume that we are trying to draw from the t distribution with 4 degrees of freedom. Our chain length will be equal to 2000, and we'll try 4 sigmas that are equal to 0.05, 0.52, and 16 respectively. You can see that as the standard deviation of the proposal distribution, the value of sigma will affect the range of the y's that we will get. If we use a sigma of 0.05, it means that the variance of the proposal distribution is really small and our y draw will be really close to the original xt. If we use a sigma of 16, it means that we will be drawing from a normal distribution with mean xt and a very large variance, and the value of y will be quite far from the current xt. We will set x0, which is the initial value, to something that's really far from the mean of the t distribution, which is 0. So let's set it to be equal to 10. This will help us see how fast the different chains with different sigmas will converge to the true center of the t distribution. All right, so the RW1, RW2, RW3, and RW4s over here essentially store the results of the Metropolis sampling algorithm, which uses different sigma values, and everything else is the same. So let's take a look at the results. The first thing we can look at is the acceptance rate using each different sigma. So this can be obtained by looking at the element k. Remember here we stored k inside each RW. We can look at each of the k's divided by n using different sigmas. And we can see that using a sigma equal to 0.05, we get the acceptance rate close to 100%. Is it good? We'll see. When we use a sigma of 0.5, our acceptance rate is around 0.85. I can't remember what the third one is, but it's a value that's between 16 and 0.5. So in this case, the acceptance rate is about 50%. And we can see that when we set the sigma to be something really large, which is 16, we get a acceptance rate about 10%. So why is the acceptance rate so low for large sigmas? So when sigma is equal to 16, why is the acceptance rate so low? Let's take a look at the plot of the Markov chains that we have created for these different kinds of sigmas. And here are the plots. The x-axis is the number of iterations, and the y-axis is the value of x. So in these plots, it plots the draw of x we get in each of the iterations for each of the different sigmas. This is the case of the smallest sigma, sigma equals 0.05, where we accepted almost all of the samples. And the last one is the case where the sigma is really large, 16. So we know that for the t-distribution, the center, the axis should be, not necessarily, they should at least be centered around 0. And let's see whether that's the case for each of these. We started at the same initial value of 10 for each of these chains. And you can see that when our sigma is very small and the acceptance chance is really high, the chain moves really slow. And after 2000 chains, it's still in the region between 8.5 and 11 point something, and it ends up around 9.5. So the chain actually didn't move much. It's not moving too close to the center of 0 for the target distribution. When sigma is equal to 0.5 or equal to 2, you can see that the chain converged from 10 to somewhere around 0 quite quickly. So these look good. And then if we look at the situation where sigma is equal to 16, then, well, we can see that the chain also got to around 0 quite fast. But if you zoom in, you will find that there is a lot of flat places over here, indicating that a lot of the x's were actually rejected. So what does that mean for us? Well, as you can see, the choice of sigma in the proposal density can affect the results and the acceptance rate. When sigma is small, which is close to 0.05, the acceptance rate is close to 100%, but the chain converges very slowly. And that's not what we want. We don't want the chain to, say, run forever for it to get to the target distribution. When sigma is really large, so when sigma is equal to 16, the acceptance rate is very low, around 10%. This is inefficient as well because most of our samples were rejected. So Metropolis Hastings or Metropolis samplers usually will require tuning. That is, we need to adjust the proposal distribution to achieve a desired moderate level of acceptance rate. A question you might ask is, what is the optimal acceptance rate for MH? You can see that it's definitely not 0 and it's definitely not 100%. Well, there's actually no golden rule for this, and it usually depends on the dimensionality of the random variable. If the random variable is one-dimensional, there's some theories suggesting that 44% is the optimal acceptance rate for Metropolis samplers. When we have a multidimensional, so a multivariate x, or some random variable we want to draw from, then some theories say that the optimal acceptance rate should be around 23%. A rule of the thumb that I usually use in practice is try to adjust the tuning parameter sigma, or whatever parameter there is in your proposal distribution, so that the acceptance rate is somewhere around 30%. If it's 20% or 40% or even close to 50%, it is fine, but I usually use 30% as a reference. And in this case, the sigma is called a tuning parameter, which is one thing that we will try to change the value and see which sigma will achieve a desired level of acceptance rate.